So in problem 72, we have 1 mole of an ideal monatomic gas at standard temperature pressure that undergoes an isothermal expansion, and so its volume increases by 2.5 times. Then heat is extracted, so it goes over this cycle. The first part is isothermal, then it's isovolumetric, and then it's adiabatic, right? And we are asked to calculate the pressure at B and C, and so on and so forth. So let's take a look at this one. So this is 72. Let's see. We have a process, isothermal, and then adiabatic. So this is PV diagram. And we start at standard temperature pressure, so this is just 22.4, and then it increases to 2.5 its initial value, which makes it 56. And so this is volume in liters. And we have the pressure, so this would correspond to actually 1 atmosphere, because it starts at STP. So which one is A? This is A, and this is B, and this is C. Right, this is not to scale, probably the figure in the book is much better to scale. And in part A, we are asked what's the pressure at B and what's the pressure at C. Right? Now I want to start by writing pretty much everything I know. So I can write the ideal gas law at these 3 points. I can write that this is a adiabatic expansion, so let's write this down. Adiabatic, and this is isothermal. So the temperature of these two are the same, volume of these two are the same, and there is no heat transfer, heat input or output between these 2 points. So I can write an adiabatic expansion formula connecting those 2 points as well. So everything I know is just ideal gas law 3 times. PAVA is nRTA. PB, VB is nRTB. PCVC is nRTC, and then VA to gamma is PC, VC to gamma. This is the adiabatic expansion. Right? So the first one is not very useful. It just relates a number of quantities that we know to each other. It's at standard temperature pressure, so you know everything about it. Now this one, however, we can simplify this a little bit. So TB is the same as TA, which is something we know. And then VC is the same as VB. So let's just reduce the number of unknowns. So this is also VB. So they're asking for PB. So it's just this, right? So PB is from here nRTA divided by a VB. Right? VB is something we know. It's 56 liters, and everything else is something known. And for PC, can we use this formula? Not really, because we don't know TC either. Can we use this formula? Yes. So PC is going to be PA times B VA to gamma. Yeah. So you just take this formula and use it to find PC. Okay, again, that's something, this actually, you know that this ratio is 2.5, it's given, and you know PA. Okay, so this is part A. In part B, they're asking to determine temperature at C. So what is TC? So this is part A. Part B, so TC, now we can use this formula because we calculated actually PC, and that's going to be PC VB divided by N times R. And so PC comes from the first part, and then you just calculate TC. Okay, so for part C, determine the work done, heat input or extracted, and the change in entropy for each process. Okay, so we calculated pressure, temperature, and volume of all the states, so I know everything about the states. Now I want to make some calculation about the processes that connect these states. So let's see if we can do that. So this is part C, the work done, heat input, and change in entropy for everything. So let's start with going from A to B. This is isothermal. So this means that there is a simple relationship. So the work done is going to be the integral of PdV, right? And I can write this pressure using the ideal gas law, is something inversely proportional, because the temperature is constant, is something inversely proportional to V. So let's do this. So P is N RT by V. All of these are constant. So this is just N RT integral of dV by V. All right, so it's just a logarithm of two different volumes, and the difference of logarithms is going to be the logarithm of the ratios. This is going to be N RT ln V2 by or VB by VA. Maybe it's the other way around. I'm not really sure, but this is something we can calculate. So the work done is given by this. So because this is isothermal, the change in internal energy is 0, and because this is an ideal gas, the change in internal energy is 0, but this is just Q minus W, so Q is just W. Okay, and W we calculated, so you already know the heat as well. And for delta S, so delta S is integral of dQ by T, but this is isothermal process, so T is just constant. You can take this out, and then this comes to Q by T. Okay, and you need to just plug numbers in. So from A to B, this is what it looks like. Now let's look at from B to C. Okay, I don't have much space, so I'm erasing, but I'm hoping you can go back and forth in the video. So for B to C, the work done is 0. The volume doesn't change, right? It's constant volume, so the work done is 0. It's 0. So the heat, so there's going to be some heat exchange over here, I guess. Do we know? So this Q is just going to be N times CV times delta T, and this delta T I know because I calculated the T for everything, and this is ideal monatomic gas, so I know that the CV is just 3/2, right? And they give us that this is just 1 mole, so N is 1, so we can also calculate this. I know everything here. I mean, I calculate the temperature, so I can take the temperature difference. That's no problem. And for delta S, which is by just dQ by T. So again, I can write this in terms of this integral, and this is going to come to just writing dq as dt. So yeah, let me just write this down, and cv dt by t. So this is just again a logarithmic integral, and this is ncv ln just t2 by t1, and so tc by tb. I'm guessing this is formula already in the book somewhere, but because you already calculate the temperatures and you know that CV is 3/2, you can also calculate the change in entropy. Okay, now what about going from C to A? Going from C to A. So this is adiabatic, which means that Q is 0, which means that the change in internal energy is just minus the work done, right? But the change in internal energy from going from C to A is the change in energy going from C to B plus the change in energy going from B to A. And these are just minus delta E from B to C minus delta E from A to B. And I can write these, right? So this is minus Q from BC minus work BC minus Q AB minus WAB. And these are things I already calculated. I calculated things for these two processes. So I can calculate the change in internal energy, which is equal to the work done in this case. Q, as I stated already, is going to be 0. And what about delta S, that well, you're coming back. Entropy is a state function, so the total change in entropy overall is going to be 0. So by the same token, since you calculate the change in entropy from here to here to here, the negative sum of those is going to give the total entropy change from going from here to here, because the sum of all of these three has to be 0, right? The entropy change from A to P plus the entropy change from B to C plus the entropy change from C to A has to be 0. Right? And you can use this to calculate the entropy change from C to A. And we can do this because entropy is a state function, just like the internal energy. Whereas these two are not. So W and Q, they depend on the path, but entropy does not. So it doesn't matter whether you go from this way or that way. And this already is something already calculated. Okay, let me just stop here.